Morning, everybody. Welcome to this webinar. So, when space comes to you, it belongs to a series of 4 webinars, which are going to take place in the following weeks. And so, this webinar is going to deal with space and climate change. And more especially, how can we use satellites to help us handle the climate change issue? So welcome, everybody. We are very happy to see you there. Thank you all for coming. So we are going to go back to the presentation. So we are very happy to have you all here. First, I'm going to give the hand to Tanya, who is the manager of the SG France 2021 event, and who is going to present the coming events for this year.
Thank you, Marie.
Tanya.
Thanks. Yeah, just as a quick reminder, so the session will be recorded. So in order to have our participant that cannot come tonight to see it again, to prepare for the event. So just a little notice. So now concerning, I'm going to talk about a little bit about SGAC and about SG France, which I'm the event manager of. So concerning SGAC, for those who might not know, but coming here tonight, it's a non-governmental, non-profit organization that is gathering some young professionals and students from the space sector. So it's basically a big organization of people that love space and that are young, as we say in the Space Generation Advisory Council. So we can see the others' activity in the other slide, but we are more than 15,000 around the world. And it allows so many activities that we can do with SGAC. So next slide, please, Marine. So concerning the different activities that we have at SGAC, so we can participate to some events as SG France, for example, but you also have and mainly have some global events, so worldwide, for example, the SGC or the SGFF, that are like events that happen next to the IAC, at the same place of the IAC, for example. And also some local event like SG France that is going to happen in 1 month. So you can also participate in some project groups that are around 10, I think, today. So there are many different topics related to space. You can have some space law, you can have some space exploration, space medicines, etc. So very interesting groups related to space. You can also develop your professional development, as it says here. You can get some mentoring opportunities there. You can have your bigger network in the space field, so it's ideal to launch your career in the field. You can also have some scholarships and some helps to go to some events or to join some space studies on space universities, etc. And finally, as the United Nations is important with SGAC because it's the main goal of SGAC to represent the voice of the young generation in space to the United Nations. So next slide, please. I'm going to talk now a bit in detail, if Pauline allows me, about SGAC in France. So there have been 2 previous events in France in 2019 and 2020 last year. And so this year's event is going to be the 3rd one. And today we have a growing community of more than 230 people in France. So it's I can only invite you to join the network so we can share our ideas about the space field, etc. So now concerning SG France 2021, which is the event that gathers us today. So it's going to be an event tackling the topic of synergies between space and non-space sectors, and basically how to bring more space in our daily life, and to create some collaborations between space and non-space fields. So it's going to happen on the 3rd of July, so in 1 month now, and it's going to be on Saturday. And in Central Lille, which is a school in the northern of France, in Lille. And we are happy because this event is going to take place on site, and we are very looking forward to welcoming you on this day. So today's webinar is going to tackle the subject of our first roundtable, which is about space for climate change. And we have our other webinar coming soon in June. The next one is on the 3rd of June that you might access today to the link, maybe if it appears in the chat. And the others are coming soon after in June. And next slide, please. Concerning now the events that are going to take place around SG France. So there is a SpaceCon taking place 2 weeks and 1 week before our event. So on the 19th of June, you're going to have a Kobo Space Program contest where you can participate as a team and try to win a very cool cash prize. And on the 24th of June, you have a more formal event where you can have some talks and conferences there. You can also meet people, startups and institutions about their sponsors, and also a pitch contest to pitch your project in front of a jury and of investors and leaders. And you have finally the Summer Space Festival, which is happening just after our event on the same weekend. So it's another reason to come to Lille in the summer. So there is this event then taking place on the 4th of July. And is a free event that you can access or online or on site. And there will be some talks also and some roundtables, so a kind of similar format on this, but also some booths and forums with the association and universities, and also companies that will be sponsoring also this event. So if you want to see their website, they are here, and we are very happy to see you there as well. Now I'll let Marine go on with this webinar's topic.
Yeah, so welcome in this webinar. We are going to see how does space help us to face climate change, and more especially, how do we use satellites and data collected from satellites to fight climate change and to understand it and to be able to better tackle it. So I'm very happy to and very grateful for our 3 experts to be there. So we have Hayley Everking from EMETSAT, who is a marine application expert. We have Daria Stepanova, who is an aerospace engineer working at German Orbital Systems. And we have Vanessa da Silva, who is working at Hydrosat as a customer relations manager. So we are very, very happy to have you all 3 here today to share your expertise and your knowledge. It's really nice. So why did we choose this subject? Is because today climate change is a very great issue. Everybody knows it. And we have more and more tools to deal with it and to tackle it. And it's quite interesting to find more about it. So first, Hayley, maybe would you have would you like to share your experience? And the slide isn't going. Okay, perfect. So what kind of oceans data is analyzed from space, and how can space help monitoring the warming of the ocean? Hayley, the floor is all yours.
Are you going to share my slides? Fantastic. Thank you very much. Hi, everybody. Thanks very much to all the organisers for inviting me today. It's a pleasure to speak to you all and to meet some new people who are interested in the space sector. My background is I work with satellites, particularly looking at our oceans. And so in these few short slides I've got to share with you today, I'm going to tell you a bit about how I got where I am working in this sector, how we monitor the oceans using satellites, and what this can tell us about the ocean's role in the climate change story. So let's get started. Maureen, can I have the next slide, please? Okay, thank you very much. So this is a bit of a whirlwind tour, I guess, through my career so far. I started off kind of just interested in general, as a lot of young people are, in how I could do something to help both people and our planet. And this led me to do a degree eventually in environmental sciences, which I followed up with a master's degree in oceanography. My logic being that the oceans are kind of the biggest part physically of the Earth system, and therefore were a good part to focus on if I was interested in solving some of these big problems that we face. And it was during this master's that I first came across remote sensing, or Earth observations, it's known as well. and I started using satellites to look at the biology of our oceans. And that led me to do a PhD in Southern Africa. I was looking to gain more experience practically working with this data and to really understand how it worked, how to develop techniques using it. And so when I was in South Africa, I was using satellite data to see how we could monitor these things called harmful algal blooms. And you can see them in the red in the picture there in the bottom right. After this, I got a job in research, working at a non-profit organization, not a university, but an independent research organization, Plymouth Marine Laboratory, where I turned my skills with satellite data into working on lots and lots of different applications, everything from human health to monitoring aquaculture, and still also keeping in touch with kind of the latest technology and how we develop methods from satellites. So a wide range of work. And that latter part of the work really took me more into what you could call the operational sphere, working with the organizations that operate the satellites. You'll be familiar with the European Space Agency. You may also be familiar with the company I now work at, which is EUMETSAT. We are responsible for operating Europe's weather satellites. And we also, as of a few years ago now, operate a number of other satellites as part of the European Commission's Copernicus program. And that's where my role sits now. So I'm an oceanographer based in Darmstadt, Germany, which is about as far from the sea as you can get, but I get to watch the sea every day using the satellites that we operate, which includes the two you see there, Sentinel-3 and Sentinel-6. So yeah, that's a whistle-stop tour of my career so far. Maureen, can I have the next slide, please? So here we've got a series of short animations, and I'm hoping if you click, it will start. Let's see. Oh, back we go. I think if you click bottom left, it should start. Nope. If it's a problem, I can share it because I've got it open on my screen. Yeah.
Sorry. I'm just gonna share this one.
There you go. Okay. So yes, one of the satellites I work with is Sentinel-3, and on the Sentinel-3 satellite, we have a number of different instruments that we use to observe our oceans. And this little animation here shows how one of those instruments work. This is the Ocean and Land Color Instrument, otherwise known as OLCI. And it basically measures, as it says in the name, the color that's being reflected from both the land and the sea and everything in between, so the atmosphere and the clouds as well. But what we're interested in using it for is to observe the oceans, and particularly the biology of our oceans. You'll see that big green patch that's just popped up there in this swath over the coast of France. So ocean color is one way that we can use satellites to gain a window into the biology of our oceans. Next slide, please. And it's another little video, so yeah, it should work. Perfect. So as well as the ocean color instruments that are on Sentinel-3, we also have a sea surface temperature radiometer. So this works similarly to the ocean color in that it's using the electromagnetic spectrum that's emitted from the Earth's surface. But in this case, we're wanting to use that information not from the visible part of the spectrum that we see with our eyes to look at the color, but to look at the temperature of our oceans. So this this sensor aboard the Sentinel-3 satellites allows us to measure both the land and the sea surface temperature to quite a high degree of precision, perfect for looking at climate studies. Okay, next slide, please. And this is my last little video. So on Sentinel-3, we also have an altimeter. This is a very different type of remote sensing. So this is an active type of remote sensing where you have a signal that's sent from the satellite down to the ocean surface. It bounces back, and we can look at the time that takes and also the shape of the signal that returns, as you can see in the animation here, to give us information about the physical properties of the ocean, such as its sea surface height or the sea level, effectively, winds and waves. You'll notice actually that this isn't sent. Sentinel-3 does have an altimeter on it, but this is actually about the Sentinel-6 satellite, which is one of the newest of the fleet of Copernicus satellites that we've had join us, and we operate this at EUMETSAT. Sentinel-6 is primarily an altimetry-based mission, so it's collecting the data as you see in the animation here. And it has this particularly high resolution mode, which is going to help us expand what we can do with this technology to look at the ocean physics properties, particularly sea level as it comes to climate change. Next slide, please. And this is the sort of data that you can get out of those instruments that I've mentioned. So in the top left there, what you can see is the global mean sea level trend since the early 1990s up towards the present. And you can see there in the different colors, the different altimetry records that we've got from various different satellites that have been observing our Earth for many, many years now. And you'll see that Sentinel-3 is just tagged onto the end. And actually Sentinel-6 is so recent that we haven't actually got data included in this yet. It's not yet been released to the public, but it will be in a few short months. So these satellites working together allow us to get a handle on what is happening with sea level and where the sea level is rising. And as you can see from this data here, it very clearly is. In the bottom left there, you can see the sea surface temperature record. So this includes data from satellites. The blue trace in particular you see there is the CCI data. This is the Climate Change Initiative, which is work done by our colleagues at ESA and around Europe, where they're producing these climate relevant records from satellite, including in this case, sea surface temperature. And again, you can see that we've had a rise in sea surface temperature over the time of the satellite record, which is what we're using to kind of track the impact of climate change in terms of warming our oceans. On the right-hand side, you can see a whole bunch of different maps, and none of these parameters that you see here are directly measurable by our satellites. However, they use a number of different satellite products combined to give us information about our carbon cycle in our ocean. Now, hopefully some of you may have heard about the term ocean acidification. This is the process where we have carbon dioxide in the atmosphere being absorbed by the ocean, and this results in a lowering of the pH as that carbon dioxide is incorporated into our ocean waters. You have this carbon cycle system that effectively creates these free hydrogen ions, which lower the pH. And this is not great news if you're a creature, for example, that's made of something like calcium carbonate, something that easily dissolves. This change in pH can affect your ability to form your shells if you're a coral or if you're a type of plankton that forms these. So it's of quite a lot of concern to life in the ocean. And using data such as that from the ocean color satellites, as well as temperature, salinity, wind, wave information, we can start combining this data to give us information about what ocean acidification is going to do over our global ocean. You can see from these maps that the effects are quite variable depending on where you are. And next slide, please. So those were just a few kind of more direct ways in which we're using satellites to look at the oceans and the effects of climate change. But by using all this data together, we can really get a whole coverage of all the different issues that are affecting our oceans and then how these interact with climate change. So everything from sea level rise and the effects on the carbon system, all the way through to things like the effects on storm dynamics. You can see hurricanes there. This is affected by the changes in the temperature of the ocean. Coral bleaching, where our oceans are warming, we can get an estimate of what's happening now, what's at risk and where, and that can inform how we manage these impacts by setting things like marine protected areas. We can obviously measure ice using satellites. We know that the sea level is rising as a result of some of the melt, but we can actually look at how the ice is melting, how that affects things like our shipping routes, for example. We can also look at the ocean's general primary productivity, as we call it, so the base level of life that's growing in our oceans. And if this changes, it can have important ramifications for us because we get a lot of our food from the ocean, and that is intimately dependent on the primary production, which we can see, for example, from ocean color satellites. Next slide, please. And this slide here, I really just wanted to show that there's a huge range of people that are involved in getting this data from space down to decision makers. It's a very long kind of value chain that we use when it comes to taking Earth observation data to decision makers. And this starts with everybody from sort of the far right of this image, places like where I work at EUMETSAT, the European Space Agency as well. Data leaves our building and goes to a variety of different expert users in research institutions, universities. They improve what we do with the data. They estimate new things from it. And then it goes further downstream into a whole bunch of different products, indexes, metrics, apps, websites, all sorts of things where the information is distilled down into the sorts of knowledge that people need in order to make decisions. And ultimately, then that's used by people in these different sectors who are responsible for things like managing the regional oceans and how they're used. So it's a very, very long value chain. And lots of people with lots and lots of different skills are involved all the way through. Next slide, please. And so I just wanted to finish up there with some links for you to see if you wanted to get involved in working with Earth observation for the oceans. There's a whole bunch of information out there from us at EUMETSAT. There's some links there from us, our colleagues at the Copernicus Marine Service who use a lot of the data that we provide from our satellites. You can get involved in working with this data in cloud computing environments more and more now. So if that's something that interests you, there's some links there. We provide a lot of user support and training, so you can contact us at EUMETSAT through our ops email address there. We have videos on YouTube, we have online open courses we've done, we have trainings where you can learn about working with the data. We have freely available Python code that you can work with to understand how you access the data and how you can interpret it. And if you'd like to apply for any courses, we have them advertised on our training website there. Other than that, if you'd like to keep in touch with me, my email address is at the bottom there, and I'm also very active on Twitter and always love to hear from anybody who's interested in our oceans. I'm very happy to take any questions that you have. Thank you.
Thank you, Hayley. That was really, really interesting. So just about the questions, I think we are going to wait till the end of the presentations to have all the other questions at the time. But if you have questions during the presentation of someone, for sure, don't hesitate. Put them in the chat. Discuss in the chat, and we will record all the questions you have, and we'll ask them all at the end, so that it's going to be easier for transition. So thank you, Hayley. That was very, very interesting. So now we are going to have Daria. Daria, who is working at Geomanipular Systems and who is an expert in atmosphere monitoring from space using satellites. So Daria, the floor is all yours.
Yeah, hi everybody. I'm really happy to participate in the webinar, and I would cover today, the next slide, please. Yeah, I will cover today the topic on how do we use small satellites and satellites for greenhouse gases monitoring. And the next slide, please. Yes, I'm coming from the German Orbital Systems company. This is the Berlin-based small satellite developer. We have a broad history of small satellites development. We had already launched 10 different satellites. We had, like most of them were for space weather monitoring and on-orbit demonstration mission. And we're really interested in the topic of application of small satellites for ecology and climate change. Next slide, please. Right, together with our partner ExoLaunch company, we pretty much provide all the necessary service for end-to-end mission development. We provide launch opportunities for different satellites or for different missions. Next slide, please. Besides the small satellites activities, we have also, like within the Space Generation Advisory Council, the Small Satellite Project Group, where the CO2 monitoring using the small satellite capabilities is also one of the core research topics. Yes, and we'll be happy if you want to join us in our research activities. Please feel free to do that. The next, the next slide, please. So that was quite quickly about the activities we're going through, and we can jump into the topic itself. So pretty much carbon dioxide levels and other greenhouse gases levels increase to new records in the atmosphere. Today, the data about GHG and CO2 emissions is collected using the big satellite capabilities, and on-Earth sensors networks. There are a couple of small satellites also, which are involved, but there are unfortunately not so many. And we definitely, we know that small satellite definitely can improve the global emission mapping coverage and image update rates, which will in general improve the understanding of CO2 and GHG dynamics. So the satellites are used to measure atmospheric concentration of carbon dioxide and methane. This information is normally incorporated into like quite complex model of atmospheric and statistical models to estimate global and regional sources and sinks of these gases. Satellites observations of Earth's surface provide data on land cover, fires, human population and infrastructure, and the biomass and biological activity of vegetation. This data is used to quantify greenhouse gases emissions from land use change and biomass burning to estimate the spatial distribution of fossil fuel combustion and to determine flows of greenhouse gases from terrestrial and marine ecosystem. The next slide, please. All right, so compared to ground-based measurements, the key advantage of satellite-based measurements are, first of all, is the ability to provide the global coverage. Satellites measurements derive atmospheric concentration of gases using the properties of gases to absorb electromagnetic radiation at specific wavelengths, and there are like 3 wavelengths for CO2, which are broadly used. These instruments primarily use solar radiation that is reflected off the Earth's surface, but some can also use the radiation emitted by the Earth or from laser on board of the satellite or from like other emitters. Satellites that absorb shorter near-infrared wavelengths are sensitive for CO2 concentrations near the surface, and therefore these have proved most useful for these applications. Another big advantages for use of satellite-based measurements are the fact that the satellites can provide fully remote monitoring. So basically you don't need to on-site operations, or you don't need any other equipment. And it's quite automated and fast estimations. And here on the slide, you can see like some of the satellites which have open data, which we're using for our models. The next slide, please. Right, detection of CO2, the average concentration of CO2 also within a vertical column of Earth's surface to the top of the atmosphere relies on measuring absorptions in 3 near-infrared wavelength bands. These bands are the weak and strong CO2 absorption bands in the vicinity of around 1.80, 1.58 and 2.606 micrometer, and for molecular oxygen, the A band is used, which is around 0.766 micrometer. Absorption of the weak CO2 band at 1.85 micrometer allows the column average CO2 to be measured because it's very little absorption by other atmospheric gases in the spectrum. Absorption can also be affected by various effects like different surface pressure due to topography or local weather conditions like clouds and aerosols. Satellites normally use 2 modes to measure this. It's either nadir mode when the satellite is looking down with the instrument, or glint mode. That's the case where instruments are angled to the point and measure the reflection from the point. So the next slide, please. On this side, you can see the some comparison of different satellites who are carrying on some of the instrumentation to measure the CO2 and in general GHG gases. We mostly use the ACO2 from JPL, GHGSat, CarbonSat, and GOSat-2 measurements. They're quite they're open for public, and they have quite good resolution and daily soundings. And they're quite many satellites to come in the near future, and especially in the field of small satellites. The next slide, please. A few words, how do we approach the topic of estimation of the carbon footprint? So basically, you have open source data coming from CO2, Sentinel, and GOSAT. With use of that data, we prepare in the carbon mapping. So basically, we collect this data, run it through some of the algorithms for filtering. We also add some ground measurements, ground monitoring station data, and we've used them together to get a little bit of better accuracy. On the other side, we use Sentinel 2 and 3, Landsat 5, 7, and 8, plus MODIS satellites to get like Earth pictures and visible spectrum, and we also use ground FluxNet stations. We run it on the right side also with some advanced algorithms. We get 2 different maps, and we developed the AI combined approach to give quite a good estimation of carbon footprint on the specific area. So this one works quite good on the regional level. The next slide, please. Just a few words about the satellites we're widely using. For example, the GOSAT 2 is just a great one. So it was launched in 2018 and 29th October. It was aiming to measure the carbon dioxide and methane at quite a good resolution with a 500 kilometers map. It has the altitude of 613 kilometers, which is perfect for our application in sun-synchronous orbit. The next slide, please. It carries two instrumentation, so it actually can measure CO2, CH4, and like some other gases. The Tanso FTC and Tanso CII, 2 instruments, and there is also the imager, which allows the automatic cloud detection and enables imaging where, like, in the places where there are no clouds. So basically, all these spectral ranges we're interested, we can get from the satellite. The next slide, please. With the use of the data from the instrumentations above, you can see what kind of maps we can generate with quite a good resolution. So that's one of the examples of the outputs of the algorithms we're using. And the next slide, please. All right. I tried to keep it quite short, and just to sum it up, I would like to say that satellite observations, they provide quite valuable information about GHG and emissions in general. Atmospheric column average concentrations of the key greenhouse gases have been measured remotely, and we're doing it and using this data on our daily basis. These measurements are being used in flux inversions to provide estimates on natural flux, and that's basically the input of our models. There are several strategies being developed to use this data to estimate the fossil fuel emissions, including the targeting of astronometers such as megacities, for example, or other different types of emitters. Remote sensing of fires, nighttime lights, and biological activity can provide global coverage needed to calculate greenhouse gases emissions from fires, estimate the spatial distribution of energy consumption, and detect large-scale patterns and trends in general ecosystem productivity. And planned future missions will definitely extend current observation capabilities, allowing long-term trends to be investigated. So the new missions which are coming, they can provide new improved capabilities, especially in terms of constellation of geostationary and small satellites on low Earth orbit to improve this observational coverage. Right. That's quite all from my side. I'll be happy to answer your questions afterwards.
Okay, thank you, Daria. This was really, really interesting, and I learned so many things about atmosphere monitoring from space. It was really, really great. Thank you for sharing your knowledge. I remind you all that if you have any questions, you can put them on the chat, and we will ask them later after the 3 presentations. So if you have any questions about highlight presentations or Daria's or Vanessa's just after this one, do not hesitate to put them there. So now our third expert is going to do her speech. So this is Vanessa da Silva. She's customer relations manager at Hydrosat, and she's going to share with us how do we handle land monitoring. So Vanessa, if you want to share your screen.
All right, can everybody see? I put this in presentation mode.
Yeah, this is great.
Awesome. Is everyone seeing that first page?
Yeah.
All right, so good evening, everyone. My name is Vanessa da Silva, and I'm here to tell you a little bit about Hydrosat and what our mission is, what we're doing to help address a lot of these climate change issues, and ultimately, the lives that these issues affect, right? So we're talking about, saving the planet, it's helping to save lives, and at the same time, all of this in a kind of commercial context, new space context, that's perhaps a little bit more agile than traditional space, so to speak. So I'll try and keep my presentations short and sweet. There's a few repeat topics that my fellow panelists have already addressed. I'll try not to spend too much time on them. I think the one thing that we can all agree on is that climate change has unbelievably negative consequences on the planet and on all of our lives ultimately. Several ecosystems are affected. We know that everything is linked between wildfires. We all know what's been happening in Australia, California, Portugal. I'm half Portuguese, so that's close to my heart. We have also a lot of the opposite, so to speak, again, of many areas that end up flooded, landslides. We're talking about areas of extreme drought, and drought that then leads to crops being harmed. And it's a little bit of a doom and gloom, but we kind of see the light at the end of the tunnel here. So Hydrosat is a company that's kind of split into two. The Luxembourg office, so where I'm calling you guys from now, focuses entirely on the data analytics. Our sister company that is based in the US, I'll tell you a little bit more about them in a second, is more focused on our hardware development. So we're kind of addressing the problem both upstream and downstream by launching our own constellation of satellites and also providing data analytics products from two separate locations. So what we're doing is we're trying to exploit a particular and unique information that we find is a little bit scarce in existing missions or in satellites that are currently in orbit, and that's infrared satellite imagery. There's a little bit of a story around this. We initially started with a little bit of thermal, and we're actually now expanding our capabilities to include a little bit more of the spectrum. So what we do is we take this proprietary data from our own satellites, fuse it with other data sources and any other publicly available data, like weather data, so on and so forth. Haley mentioned earlier Sentinel, that's one of the data sets that we use. We also use Landsat, MODIS, and so we bring all of that together to create a more complete image than any one single source would be able to give us. And of course, this has applications that are quite extensive in many different areas, including agriculture, being able to help farmers irrigate their fields properly, being able to predict yield. And so these are the two commercial products that we are currently focusing on under contract with the Luxembourg Space Agency. Yes, we are small, but we have our own space agency, and ESA, and that everyone here, I imagine, is familiar with. So this kind of completes a little bit that story of why Hydrosat is particularly keen to exploit thermal data. So you see here that we have so much data available, both from agencies, space agencies, national space agencies, institutions, but also a lot of fellow new space companies, often very young and dynamic and forward-thinking companies such as ourselves, trying to find gaps in our knowledge and how to fill them. However, what we notice is that no one is really going for thermal that is good enough, let's say, for, again, commercial applications. So some of the missions that I mentioned before, like Landsat, do not provide enough spatial or temporal resolution, and particularly at a price point that is, let's say, interesting or achievable, affordable for a lot of people. Just to give you guys a bit of a frame of reference, Landsat missions cost several hundreds of millions of dollars each. And typically what happens is that the actual sensors themselves require cryocooling, right? So that means suddenly you have this satellite that is huge. We know that launching, more mass is, equals more dollars. So what we're doing is we're actually developing our own instrument and cutting down on costs. And we have found a way of achieving that higher spatial resolution, that higher quality of image with a higher revisit time for a very small package. So you'll see here at the bottom left of my screen is a picture of our very first thermal sensor. We very recently, as recently as December 2020, finished developing it. What you're looking at there in the middle is a high altitude balloon test of that sensor. So the image to the right is a real image from that test flight, and you're looking at salt flats in the US. And then there's a little subset of that image where I've overlain the actual thermal data so that you can compare, what we can see with visible versus thermal. So that was actually quite cool. That went really well. We got a lot of good data out of it that we're still working our way through. And we are on schedule to launch our very first satellite in the summer of next year. So in order to kind of align with launching of our hardware, launching of our flight segment, we are also working, as I mentioned previously, on a couple of commercial products. And I call them commercial, by calling them commercial, I'm not limiting myself to, mentioning customers that are in the private sector. We do work with a lot of governmental institutions, a lot of policymakers, and it's really interesting that we can get, this much high quality data into the hands of people really quickly and enable that informed and rapid decision making. So this slide here has a couple of screenshots of our very first prototype of our crop yield forecasting tool. So in essence, I don't want to spend too much time on this, but in essence, we gather data from multiple sources. And I also can't share, for proprietary purposes, this is our edge, and build these maps that allow people to navigate to whatever it is that they're trying to look at. So there's 3 screenshots in here. I think one of them might be a little blurry, but going from top right corner, you're looking at the yield map. So we're looking at the US, and you can go by state level, county level, national level, and find out what data you're looking for. So how much yield, so in other words, how many bushels per acre did you get in a particular year for a particular crop? And then, then you can take that information, which is also, the second screenshot there in the middle feeds into that first one as well. So we're looking at crop classification data from last year. So that's looking at different types of crops. So here we've just started with corn and soybean. So again, this is a first prototype with real actual data. And then in kind of a light green or olive green is just anything else. So you can see there quite high resolution. You can even zoom in on this map and see exactly what is being planted where. The third screenshot at the bottom center of the screen is a vegetation map, also for last year. So same thing, you can use filter through which area you want to look at, look all the way down to county level, and get whatever insights you're looking for. All of this data can then be aggregated in the form of, or presented in the form of, tables of data or, visual, if you need visual aids, being put together in a graphical format. And what we're aiming to do this summer is run a live test. So during this growing season, run live tests and see how well we do. At least back testing has gone really well. But of course, people that are looking to use our tools are interested in knowing that we didn't fudge our numbers, right? And show them in real time that we are able to very accurately predict what yield is going to be this year. And then of course, in the future, we're going to expand these maps to include different crops, different geographies, and the priorities of which will need to be driven by what resource we have and what is, of course, commercially interesting to us and what's doable. So that's the first one, the first of the two projects that we're working on under that same ESA contract. But really the second one, I think, is a little bit more relevant to what we're talking about here today. So the second one is irrigation management. So us being able to essentially give farmers, growers, or any chamber of agriculture, or any decision maker, any policy maker, the tools to know exactly how much to water, how much to irrigate their plants, and when and by how much. And this is critical. Plants, they are similar to us humans. Too much or too little food, not good. So you really need to optimize that. We kind of based a lot of this work on some solid research that NASA carried out. And they've said, and they've found that optimizing that irrigation, so again, not over or under watering, can actually increase your yield by 20%. Now, 20% is huge. So essentially for less water or for optimized water usage, you get 20% more. That's 20% more that you can, redistribute, that you can help or use to help address, food security issues, for instance, all the while, helping with water conservation. So it's really two birds in one stone. And the groundwork for this is measuring temperature, right? And measuring temperature of these fields, measuring temperatures of these plants, understanding what the soil, plant, moisture, environment, weather dynamics are. And through, again, our proprietary algorithms, we can crunch all of those numbers and essentially get to these really, really valuable insights. So what you're looking at over here is a potato field. It's in Germany. I forget the exact name of the closest town, kind of in the middle of nowhere in Germany, maybe a 3-hour drive from where we are now. And what you're looking at is the relative temperature between the crop and the air. So it's a relative temperature. It's not an absolute one. Otherwise, those would be very cold potatoes there. And really unfortunately, I can't share much more, this company secrets. But really these are three big conclusions that we were able to draw from this experiment and others that we are running in parallel. We know that insufficient water, definitely has a negative impact on yield. So those areas in the picture that are, yellow and orange and red are areas that were purposefully, kept a little thirstier. We also know that there is a particularly good time of the day for irrigation. So again, when to irrigate. So I'm talking about time of day. We also know that being able to detect that water stress and that soil moisture can help feed into that calculation of, optimized irrigation. And we were able to do that. Again, this is a drone image. So, our first satellite only launches next year, but we correlated this with a lot of ground measurements, gathered a lot of ground truth data. And so we're feeling really positive about this particular product. One more slide here on our irrigation work. So our next steps for that particular project is going to be scaling the data that we're using to use, satellite instead of ground or drone measurements. And then being able to fuse that with other and multiple sources to get even more accurate insights. As I mentioned before, our first satellite goes up in June of next year with Loft Orbital. And we do have future planned missions, but that's a watch this space kind of moment there. So we've started with yield and with irrigation. These seemed like quite pressing issues and issues that we were well equipped to address in the short to medium term. But we also have a few other projects that are simmering in the background and just waiting for a little bit of resource. So, there are so many things that can be done with different areas of the spectrum, with different instruments, with different technology. But really what Hydrosat is interested in essentially is water. And we know that infrared is a key component to addressing a lot of these challenges. And by looking essentially at the temperature of either the ground or even the ocean or any body of water, it could be riverbeds, we can address a lot of these problems. So we've done a couple of preliminary studies with some partners on wildfires. And with our high-res, high-revisit time maps of the world, we can actually predict before they happen, we can actually predict where wildfires are going to occur. We can help to monitor them and do burnt area assessment afterwards. So that's the before, during, and after of wildfires. And you can imagine how helpful that can be to manage those situations. We can also help to predict droughts, and that kind of data can feed back into our yield forecasting tool that I showed you guys earlier. And another interesting project that's coming, knocking on our door is studying permafrost. So there's this, kind of vicious cycle of thawing permafrost, whereby, a lot of the microbes that are captured within it start to release methane, and then the methane, allows temperature rise, which, in turn releases, causes more microbes to release more methane, and so on and so forth. So that this is another area that could potentially be interesting to us. That is it for me. Thank you for listening. Looking forward to your questions.
Yeah, I thank you for this presentation, Vanessa. This was really nice and really interesting. Now I would like to have to ask the questions you've mentioned in the chat to you ladies. First, there's a question for Daria. So which wavelengths are the satellites using to take every information from the ocean? Okay, this might be more for Hayley.
Yeah, I think so. So depends a little bit on which of the satellites we're talking about, or rather which of the instruments But of the two that I talked about, or two of the ones that I talked about for ocean color and for sea surface temperature, the wavelengths for the ocean color, you're looking between about 400 and 1,000 nanometers. And for ULCI, the sensor we're looking at, you have 21 different bands. They're relatively narrow, and they have a specific response function that's helpful to look at the ocean, which is quite a dark target. And you need to have these quite narrow ones so you can pick out these weird features in the spectra to get the information you need. So that's what we have on that. For the sea surface temperature, it's from about 550 to about 12,000 nanometers. So it's much more towards that end of the spectrum with the thermal and the infrared and everything. And that has about, I think it's about 6 or 7 different bands, some of which are used more for correcting for the atmosphere, and some are used to detect fires as well. But so, yeah, a range of different wavelengths.
Okay, great. Thank you, Haley, for sharing this information. Now a question really for Daria. Does each new EO satellite launch employ a novel sensing technique, or are we launching more simply to increase coverage?
That's a really good question. So the different applications require different configurations of satellites. I think the best approach would be to use some kind of fusion to have like really good resolution of imagery using the like big satellites and having a rapid response in terms of imagery acquisition from small satellite constellations. In that scenario, you can have the global coverage with a medium resolution, and you can track like long-term changes while still being able to like get a focus on specific regions with a much better resolution. So yeah, my answer would be the fusion of different types of data.
Yeah, so this really depends. Vanessa, could you tell us how would the data be used in a disaster management, like in case of a big crisis?
I can comment on this a little bit if you want.
Go ahead, Haley.
From the METSAT perspective. So, I mean, the ocean stuff in part is used towards disaster management, particularly with regards to things like weather prediction or looking at things like storm surges, tsunamis, and things like that. But as an organization, we obviously provide a lot of direct weather data as well. And we're actually part of this disaster management charter, which gets activated whenever there's an event around the world, and we get data out to people as quickly as possible. And a lot of the high resolution optical data, not the stuff that we work with, but that's available from other satellites like the Sentinel-2s, for example, Landsat and things like that. They can be quite useful in disaster planning in terms of response, looking at what's actually happened on the ground and strategically figuring out where you need to deploy your resources. I don't know if any of the other speakers can maybe comment on this a bit more as well, probably.
Okay, nice, great. Thank you. Now a question from Florian. Who are the main customer for your data and your analysis? So maybe the three of you could answer these kind of questions. Are they more for firms or for like individuals?
So from Hydrosat's perspective, there's a wide variety of them, and it depends for which applications. So our yield forecasting, for instance, tends to be a lot of agribusinesses, so food producers. We're talking a lot about insurance firms, insurance companies, a lot of governmental institutions. Whereas when we talk about irrigation, it's more interesting and more relevant to farmers and agricultural policymakers. So cooperatives or any association that groups several farmers together, those are the people that we would reach out to, probably through partnerships, channel partnerships. We're a small startup. We do not have the manpower, the human power to go and reach out to thousands of individual farmers directly. But the idea would be really to reach those people. And then as for a lot of the other projects that are a little bit on the back burner now, waiting for a little bit more, a little bit more cash to be developed into something viable, It will depend. It will depend. You know, we were talking about disaster management, so things like wildfire predictions. There's a lot of forest management associations. Those ones will tend to be a little bit more, you know, on the governmental side, but a lot of commercial entities are also interested. It'd be quite surprising, but a lot of them have, let's say, a vested interest in monitoring what is going on with different portions of land. And they make a lot of, you know, trading decisions, you know, by looking at data over, you know, years and years and years. And if we can give them, you know, highly accurate predictions, that can save them a lot of money and make their operations more efficient. So it depends a lot. And I guess, you know, long story short, pretty much everyone can be an end user of all of these data products.
And now a question from Triti Aradia. Is there a particular place on Earth where the maximum amount of CO2 is present? Maybe you know that, Daria? Like the maximum CO2 rate, do you know where in the world?
That's an interesting question. Like the thing is, so the concentration is constantly changing. So it's in every time, in every moment in the time, there's probably another place somewhere. And it really depends on the time on the year. So with summer, winter, in which hemisphere, it really depends on the concentration. So I would say somewhere in July, somewhere in northern hemisphere, depending on the winds and on the atmospheric pressure and the clouds, there might be some place, but like I'm not sure that this place there is any place with the highest concentration. But it's an interesting question.
So not yet identified, but could be. Great. And now we have a question from James. Do the satellites have a method of staying in orbit, or are they intended to return back to Earth through orbital decay? So maybe Haile or Daria?
Yeah, I can probably comment on this. So yeah, they do. I mean, they have fuel on board, so you can move them to a point. Obviously, you don't want to be launching extra fuel into space more than you need because it's weight. And as Vanessa was saying, weight costs money. I think it was what Vanessa, maybe or Daria, one of the two of you was saying about how the heavier things are, the more it costs to get them up there. So you have to be quite careful with what you do. You don't want to be moving them around all the time, but you can use fuel to maintain the orbit for certain amounts of time. But they will, depending on where you launch them as well, you can basically make the calculations so that they will stay up for as long as possible with minimum need for adjustment. And then eventually the orbits are planned to decay. In most cases, I think somebody also asked about space debris, and this is one of the things that we have to focus on a lot now. We have colleagues over at ESOC here in Darmstadt at ESA's Operations Center that work a lot on space debris and how we can manage where we put our satellites when they're dead, effectively. And one of the ways is to bring them into other orbits or to drop them through the atmosphere so they burn up and decay before they come back to Earth. So.
So quite a technical question. And so now another question again for Daria. Is there any possible ways to make the ocean stop taking carbon dioxide? Or more for Haile, maybe?
Possibly one we can both talk about a bit, I guess. In a way, you don't really want to. The fact that the ocean is taking up so much carbon dioxide is really helping us to avoid a lot of the problems, or worse problems rather, from climate change. The oceans are a great sort of sink of where carbon dioxide can go. You can affect how much carbon the ocean takes up by changing its temperature and by changing the chemistry. But it's kind of, to actually do that would be really, really difficult, and you probably would create a lot more problems than you would solve. So yeah, you could probably do something to change the chemistry in certain parts to make it absorb more or less. That's kind of how the carbon buffer system that we have already works to a point. But you wouldn't want to, I don't think.
So this one is really important. Why do we stick with carbon? What about other compounds? So maybe are there other compounds that could be analyzed to check the pollution in the atmosphere?
Yeah, we do also analyze the methane, but these two gases give pretty much a good overview on like on the status. There are also like other gases which are being monitored. Yes, for example, you can also monitor NO2 or like CO, but most of the instrumentations are mostly focused on carbon dioxide and the methane. Yeah, but yeah, it's possible to monitor other gases also.
Thank you. And a question from Ashish Dura. Is there a way to know the sea's most polluted area? The same as for CO2, but for the sea.
Yeah, so we can look at, it depends what you mean exactly by pollution. We can do things like we can detect oil quite readily from space now, particularly using synthetic aperture radar. I didn't talk about that as a way of observing the ocean, but it's becoming more and more common to see that being used. You can also use optical data like the ocean color, but it's not as good because you can't get through the clouds, whereas the synthetic aperture radar can. So you can use that to look at where you have pollution from things like oil. We can also look at sort of the impacts of certain types of pollution. So we can look at where we've had a lot of agricultural runoff, for example, so fertilizers and things being washed into the sea. You can see this because of the effect it has on the algae. It tends to make them grow. So you get this eutrophication, they call it, like a lot of green algal growth in different areas, and that we can see from space. In terms of any other sources of pollution, debris and things like that, you can look at where they would be most likely to accumulate based on things like ocean currents. If you've got high resolution data, you can sometimes see like larger accumulations of debris as well. So there's a number of different ways we can look at it.
Okay, thank you. So satellites are very useful in that case. Mm-hmm. So there's a question here from Thibaut, which is quite technical. Which data have you used to train your neuronal network allowing the forecast yields? So I think this is for Vanessa. Like, what is the let's say the data path for?
What was the question? What was the data source? I didn't hear. Which data have you used to train your neuronal network allowing the forecast yields? So a lot of the, let's say the ingredients, right, to our magic sauce are a lot of publicly available data sources. Sentinel, Haley mentioned Sentinel earlier, Landsat and MODIS are kind of our go-to. And then in terms of, how we train our algorithms, that's proprietary info, that's company secret. But if the question is what sources of data, those are the main public ones. And of course, once we launch next year, our own.
That is really great. Here I have a question for Daria. So there is a high rate of CO2 in the atmosphere. Do you think there is a way to use it? To extract the CO2 from the atmosphere to use it, for example, in catalysis?
Interesting question. I'm not a chemist based on my background. I'm more a satellite developer. I'm sure there is a way, but I'm probably not the best person to answer this question.
Okay, here there's a question again about computers. So which technology do you use to process data? Python or others? And are you using AI for your different products? Maybe Vanessa, are you using AI in Hydrosat?
Yep. So similar answer to previously given. A lot of that machine learning is proprietary. So everyone has their different methods, and their, writing algorithms is kind of it's a science and an art, and there's many ways of doing it. And we have our own kind of magic secret sauce. But yes, we do code in Python if that's the one that was mentioned. We also are in the process of securing a longer term agreement with AWS, for instance. And I know that Luxembourg recently put out a call for proposals around their Melusina project, so high performing computer. And so we've applied to that as well. So I'm sorry for the very vague answers, but we're a startup. We've existed for less than 2 years, and thankfully, it's a good thing. Competition's a good thing, but there are many other people that are trying to do similar or related applications. So we need to keep our edge for as long as we can until we're ready to commercially launch our data products. The idea is to have that happen roughly at the same time as our satellite launch next summer.
So this is coming very soon.
Yeah, sorry, if I tell you, I'd have to kill you.
I'll say a word. And so last question, because we will soon finish. Is there a way in which we can rely 100% on satellite data? Dia, you talked about many different things that can alter data we collect in satellites. So how can we increase the precision of satellites?
All right. Yeah. So there are basically two approaches for mapping, for carbon mapping. You can use bottom-up, top-down. One involves the satellite data, which you apply together with the models, and based on that data, you can estimate how much carbon is in the atmosphere. Another way is to use the data from the base station, ground stations. So basically, the best is the most accurate approach would be to use both of these approaches together and find some also place for the fusion here, minimizing the error of each of that one. So I would say satellite data alone is not enough for proper estimation of carbon in the atmosphere. So you definitely need ground stations.
Yeah, and if I can add a side note to that, the perspective of our irrigation yield and other, in the making projects, we have to kind of use a variety of sources of data. I don't think that any one particular band or any one particular, whether it's space-based or Earth-based, can give you the full picture. Now, which data sources you use and which technologies you can further develop to get to the answer you need is dependent on what you're trying to do. So for instance, for our irrigation management, we use a lot of ground data as well. Not only to not only to prove that we can use or that the satellite data is useful, but also to complement it.
Okay, yeah, great. So we saw applications on the atmosphere. So this has been really nice on land applications, of course, with Hydrosat, and also what sea and oceans application can be made. And this is really nice to see all the kind of things we can do with satellite data. So unfortunately, the quiz didn't really work, so I apologize for that.
Excuse me, Marine. We have some winners actually, because we have had 4 answers. But next time I will make sure that the link is working well. You just need to update the page because
yeah,
my bad. Yes, next time we will make sure that the link is working for everybody. So if you guys want to get the chance to win some gifts, will be all right.
So the team Marwal, very French team. The team Marwal just won the competition. So congratulations to all of you. So we will contact you for you to receive the gifts. And now, just for 2 seconds, this webinar is a part of 4 webinars which are taking place. So this one end of May, and the 3 others are going to take place in June. And the next one is going to be on the 3rd of June, and it's going to be dealing with sustainable development in space, and how do we monitor and use the space and satellites to develop sustainable development on Earth. And our on-site event is going to take place on the 3rd of July, and we are very happy and about it, and hope to see those of you who would like to come. So thank you all for coming. Thank you to our 3 wonderful experts who have been sharing their time and their knowledge during all this day. Okay, thank you all, thank you everybody, and we hope to see you another time in SJC webinars. Thank you, goodbye.